Welcome back, everybody. Let's do another linear algebra example. So let's recall the definition of linear combination. So a vector b in Rn is a linear combination of the vectors v1, v2, all the way to vp in Rn. If there exist scalars c1, c2, all the way to cp, such that c1 v1 plus c2 v2 plus plus cp vp equals b. So how do I solve such a vector equation? Well, I'm going to use an augmented matrix. Remember that the columns correspond to v1, v2, all the way to vp, and after our bar, well, that's where b goes. If I needed to find the specific solutions to c1, c2, etc., I would row reduce completely. Remember that a system is consistent if there's no pivot in the final column of the augmented matrix. So if I row reduce and I found a pivot in the final column, that's bad. The system would be inconsistent and I'd have no solution. So with that said, let's go ahead and take a look at an example. So let's say I want to determine if the vector w is a linear combination of the vectors v1, v2, and v3. Well, by definition of linear combination, I really want to know, can I find solutions c1, c2, and c3 to this? Well, what's my method? I'm going to use an augmented matrix. The columns correspond to the vectors v1, v2, v3, and then after the bar goes w. So let's fill that in. So our first column vector v1 is the first column, v2, v3, bar, and then column vector w. Okay, let's go ahead and start to row reduce that. So we've got a leading 1 here. Let's use that to get a 0 here. So we're going to follow this recipe, 2 times row 1 plus row 2. That sum replaces row 2. Okay, so remember that row 1 stays the same. It's row 2 that's changing. Okay, so that'll be 2 plus minus 2, 0 plus 5, 4 plus 0, negative 10 plus 11, and we said that row 3 stays the same. Okay, so this seems good so far. Let's go ahead and use that leading 1 to get a 0 right here. So we'll do negative 2 times row 1 plus row 3. That sum will replace row 3. Okay, so it looks like row 1 and row 2 are staying the same. Okay, so that's going to be negative 2 plus 2. That's 0. We've got, looks like 0 plus 5. That'll be negative 4 plus 8. And that'll be positive 10 minus 7. So that's 3. Okay, we can actually use row 2 to get some zeros here in row 3. Let's do that. So let's do minus row 2 plus row 3, and that sum will replace row 3. So row 1 is the same, row 2 is the same, and let's see what our new row 3 looks like. So that's going to be 0 plus 0, negative 5 plus 5, negative 4 plus 4, and then negative 1 plus 3. But let's notice something. We've got some very clear pivot positions. So that's a pivot position. That's a pivot position. Why is that a pivot position? Because if I continue to row reduce, I could get a leading 1 here. So that makes this a pivot position. And this is actually a pivot position as well, because I could get a leading 1 there. So that's a pivot position. Well, that's bad, because if we have a pivot position in the final column of the augmented matrix, so then there's no solution. So let's say since there is a pivot position in the final column of our augmented matrix, there is no solution. And thus, if we look back at the original, let's fold this just for context. And thus, W is not a linear combination of V1, V2, and V3. So yeah, this pivot position in the final column said you'll never be able to find C1, C2, and C3 such that the linear combination equation holds. And again, if you're unsure why this leads to no solution, just think about what the last row says. The last row says 0 C1 plus 0 C2 plus 0 C3 is equal to 2, or 0 equals 2. That's a contradiction. Okay, so with that said, let's go ahead and try another example. So if possible, express the vector B as a linear combination of the columns of the matrix A. So first we want to remember that the columns of a matrix can be thought of as column vectors, right? So let's call V1 the first column as a vector, so the vector 1, 0, 1. V2 is the second column, so negative 2, 3, negative 2. And V3 is the third column, negative 6, 7, 5. So just using the definition of linear combination, we want to solve, if possible, this equation, right? So you want to have this in mind. As soon as you see linear combination, by the definition, you want to have this equation in mind. Are there solutions? Can I find C1, C2, and C3? That's what we're solving for. Method, again, augmented matrix. The columns are the columns of A. Those are our column vectors. Remember, the C's are numbers, they're scalars. But in this case, we want to actually find C1, C2, and C3 because they're saying, if possible, express this vector in such a way. So that means we want to explicitly find C1, C2, and C3 in this case. So you have to be careful what they ask for. Okay, so let's go ahead and set this up. So right here for V1 should go, that's our V1. V2 will go here, V3 will go here, and B will go right here. Okay, so here we go. So V1, V2, V3, bar, and then B. Okay, so we want to row reduce this. We actually want to be able to write B as a linear combo of V1, V2, V3 if possible. So we're going to row reduce. So for free, we've got this leading 1 right here, so that makes this a pivot column, so we should probably get a 0 right here. So let's do minus row 1 plus row 3, and that sum is going to replace row 3. So row 1 stays the same. Row 2 also stays the same. It's row 3 that's changing by this little recipe here. So that looks like minus 1 plus 1. That looks like 2 plus minus 2. And that looks like 6 plus 5. And then here, this could be 14 minus 3. So right now, let's notice some things. Look specifically at the coefficient matrix right here. Notice that I've got a pivot position here, a pivot position here, and a pivot position there. Remember, the pivot positions correspond to leading ones if I were to reduce further. The fact that every column in my coefficient matrix has a pivot position tells me I'm going to have a unique solution. Now in this case, I would be happy if there was either a unique solution or infinitely many solutions. That would be okay as well. But by virtue of the pivot positions in the coefficient matrix, I can tell there's going to be one unique solution. Okay, so let's find that solution. Let's reduce further. So let's get a leading 1 right here. Okay, so let's go ahead and use this leading 1 right here to get zeros above. So let's do -7 times row 3. Let's add that to row 2, and let's have that sum replace row 2. So row 1, of course, stays the same. And let's see what's up with our new row 2. So that's going to be 0 plus 0. That's going to be 0 plus 3. That's going to be -7 plus 7. And that's going to be -7 plus 16, which is 9. That seems pretty good. Okay, so let's get a 0 here, and then we can take care of, we'll take care of that after. So let's get a 0 right here. Let's do 6 times row 3. Let's go ahead and add that to row 1, and that sum will replace row 1. Okay, so that'll be 0 plus 1. That's going to be 0 plus -2. That's going to be 6 plus -6. And that's going to be, let's see here, so that's going to be 6 minus 14. That looks like -8. Okay, so I've got a pivot position right here. Let's go ahead and get the leading 1 there. So 1/3 of row 2. So row 1 stays the same. And for row 2, we've got 0, 1, 0, 3. And then row 3 was 0, 0, 1, and then 1. So great, we've got this leading 1 here. Let's go ahead and finish out the reduced row echelon form by getting a 0 in that position right there. So let's do 2 times row 2, add that to row 1, and that sum will replace row 1. Okay, so that's going to be 0 plus 1. That's going to be 2 plus -2. It's going to be 0 plus 0. It's going to be 6 minus 8. So 6 minus 8 is -2. And that's looking pretty good. Okay, so this is in reduced row echelon form, so that seems really good. And so remember, this corresponds to C1, C2, C3. So that means that C1 is equal to -2. So here, C2 is equal to 3, and then C3 is equal to 1. Let's go ahead and check our work. Actually, and we should really address the question because they asked us to, if possible, express B as a linear combo of the column. So let's do that. So B is equal to C1 V1 plus C2 V2 plus C3 V3. And so to address the question, that would be B is equal to C1 times V1 plus C2 times V2. And V2 we said was what? -2, 3, -2. And then C3 was 1 times V3. So that addresses the question. If possible, express B as a linear combo of the columns. We did. So that would be the answer. And of course, we want to check. That's one nice thing about linear algebra is a lot of these are very, very checkable. So all we have to do is perform this computation and see if we get this vector out. So let's do that as a check. Okay, so here's B. Okay, so remember how to scale a vector. So each component gets scaled by -2 here. So it's going to be -2, 0, -2. Here, each component gets scaled by 3. So that's going to be what? -6, 9, -6. and here every component gets scaled by 1. Okay, so now we just remember how to add vectors. Well, to add vectors, they all have to be from the same Rn for some fixed n. So they're all from R3, so we can add them. Right? They're from different spaces. I can't add them. So what do we have here? So this is going to be -2 -6 -6, 0 plus 9 plus 7, and then -2 -6 plus 5. And let's see what that gives us. So that's going to be -14, 16, and that looks like -3. It checks. So that's good.